Hello everyone. In this video, we'll be talking about the propagation of the radio signals. It happens via three modes. Number one is the ground wave propagation, number two is the sky wave propagation, and number three is the space wave propagation. We'll learn their details one by one. But before that, let's have a look at the transmitting antenna. For efficient transmission of the radio signals, the length of antenna is integral multiple of the lambda by 2, and the simplest antenna which we use, they are known as the dipole antenna. Okay, so L should be equal to n lambda by 2, where n is a positive integer 1 2 3. Got it? Now let us look into the details of the ground wave propagation. It is used primarily for the frequency range 30 kilohertz to 3 megahertz. The ground wave signals are having the vertical polarizations and they follow the contour of the earth. Since earth is a conductor, the ground wave radio signals induces the current in the earth, and as they travel far and far, their energy content keep on decreasing. So the attenuation in the ground wave signals is the maximum among three possible modes of the propagation. Got it? The best transmission of the ground wave signal occurs over the salty water, because the salty water has more conductivity as compared to the earth, and the range of ground wave propagation is smaller as compared to the range of the sky wave propagation and the space wave propagation. Now let's talk about the sky wave propagation. This mode of the propagation of the radio signals is preferred for the short wave broadcast, means the frequency range 3 megahertz to 30 megahertz. Let's have a look at this picture. The ionosphere extends at a height of 50 km to 400 km above the earth surface, and this ionosphere is usually divided into four layers: D, E, F1 and F2. The D and E layer, they exist only during the daytime. F1 and F2 layer exist all the times during the day as well as during the night. As we go above the earth's surface, the density of air decreases, but the degree of ionization increases. Got it? So the different layers in the ionosphere will have the different densities of the ions. Clear? Now the sky wave signals are radiated into the atmosphere, and since the ionosphere has the different degree of the ionization, these signals are bent down towards the earth. Keep in mind, here the refraction is happening. Many people have a misconception. They think that from the ionosphere the radio signals are being reflected, which is totally wrong. Here the refraction is taking place, and the bending of these radio signals can easily be explained using the Snell's law. Got it? Let us look at few radio signals. The signal which is sent straight vertical does not bend at all, while as the signals which are making smaller angle with respect to the earth's surface, they will bend more. You can see this diagram very clearly. Usually higher the frequency of the signal, the less radiating angle is required for the bending down. These are few good informations which we should learn. Beyond the 50 megahertz frequency range, the sky wave propagation doesn't work. Got it? Although during the sunspot activity or few unusual electromagnetic phenomena, the high frequencies such as UHF, ultra high frequency, or VHF, very high frequency, or even microwave signals can be bent down by the ionosphere, but this is very rare. Got it? In the sky wave propagation, the loss of the signals is minimum and the range is great as compared to the ground wave propagation. Got it? You may note down all these informations and then we'll go further. Sometimes the signals coming from the ionosphere are reflected by the earth and then they are sent back to the ionosphere. From there, they again bend down towards the earth and then again reflected by the earth toward the ionosphere, and this keeps on happening. This is known as the multiple hop transmission. In ideal atmospheric conditions and the sufficient strength of the radio signals, there can be as many as 20 hops, and by this multiple hop transmission, the range of the radio signals can be extended up to several thousand kilometers. Got it? Note it down, then we'll go further. Here is a simple question on the board. We have two radio signals. One is of the frequency 5 megahertz and the other is of the frequency 8 megahertz. Okay. Question is asking which radio signal will travel a greater distance in the ionosphere. You can pause here and think about the answer. Okay. The correct answer is the radio signal of the higher frequency, means 8 megahertz, will travel more distance in the ionosphere. The reason is simple, it has more energy, so it will penetrate more layers of the ionosphere. Got it? You may note it down, then we'll be taking up the second question. Here is the next question, and it is just a formula based question. So if you wish, you may pause the video and do the calculations, and then I'll be simplifying the things on the board. Okay, I hope you got your answers. So let us see the solution here on the board. Suppose we calculate first for the F1 layer. For F1 layer, the frequency of the radio signal is given as 5 megahertz. So 5 into 10 to power 6 hertz is equal to 9 root n max. According to the question, do you agree? It's a simple mathematics. Do the calculation, you'll get the n max. Got it? Now for F2 layer, we can do the same calculation. The frequency of the radio signal for F2 layer is given as 8 into 10 to power 6 hertz. Actually 8 megahertz I am writing as 8 into 10 to power 6 hertz. For calculation purpose, I am omitting the units. 9 root n max. So when we do the computation, we'll get the n max. Now in the final answer, we'll be putting up the units. Got it? It's a usual practice while doing numerical calculations. You can skip the units if you are working with the SI system everywhere, and then in the final answer you put the unit. Okay, note it down. Then we'll go further for the space wave propagation. Now let's talk about the space wave propagation of the radio signals, or the line of sight propagation. Let's have a look on the board. This mode of the propagation of the radio signals is usually preferred for the frequency range greater than 30 megahertz, means very high frequency, ultra high frequency, the microwaves. Okay, suppose there is a tower on the earth surface. The height of this tower I indicate as HT, and this is known as the radio horizon DT. Okay, now to receive the signal somewhere here, we install the receiving antenna. Let's say its height is HR. Height of these antennas may be different. Okay, and this is known as the radio horizon for the receiving antenna. We call it DR. Why it is known as the line of sight communication? Signal is traveling straight from the transmitting antenna to the receiving antenna. This signal is not bending. This signal is not following the contour of the earth. Got it? Now this entire distance is known as the DM. DM means the maximum distance for the line of sight communication. and it will be almost equal to root 2 REHT, where RE is the radius of earth, HT is the height of the transmitting antenna, plus root 2 RE, height of the receiving antenna. This is an important expression. I'll derive it. Let's do that here. We consider here an antenna of height HT and the radio horizon is DT. This is the RE, the radius of earth. Similarly, this distance is also RE. Do you agree? The radius of earth. Now we can see a right triangle here. In this right triangle, we can use the Pythagoras theorem. So what we should write? The dt square plus re square, dt square plus re square is equal to ht plus re whole square. Do you agree? Now simplifying it further, opening up the whole square, so we should write here ht square plus re square plus 2reht. Okay, radius of earth is around 6,400 kilometers, and with respect to the radius of the earth, the height of this transmitting tower is negligible. Okay, it means you can neglect it. This re square is getting cancelled out here. Then we are left with dt is almost equal to root 2 REHT, and in the similar way we can derive the expression for the dr. Got it? And dt plus dr will give us the dm. Pretty simple calculation. Another important result for this transmitting tower is the area covered by this transmitting tower. That area will be simply pi into dt square. It will cover a circular area on the surface of earth. Got it? You may note down all these informations and then we'll be taking up questions on that. Here is a simple question, formula based only. So if you wished, you may pause here and try to obtain your answer. I am doing the calculation on the board. We know that dm will be equal to root of 2reht plus 2re height of the receiving antenna. Okay, it is almost equal to this expression. Now we know all the values, so we can put up the values. Root 2 into re is 6400 into 10 to power 3. ht is 32 plus 2 again 6400 into 10 to power 3, and hr is 50. I told you that receiving antenna and the transmitting antennas can be of different heights, can be of different lengths. Doing this entire computation, will be getting a 45.54 kilometer. That should be our answer. Okay, I hope you got the same answer. Note it down, then we'll be taking up the next question. Here is the next question. It's a good one, so if you wish, you may give it a try, then I'll be simplifying it. I hope you got the correct answer. The number of antennas is 6 and the HT will be equal to R. These are the final answers. Let us prove that. Here is the earth. The radius of the earth we consider as RE. Now, in order to cover up the entire earth, there will be 6 antennas required. Think about it. One antenna here, another antenna here, another one here, and then fourth one here. And since earth is 3-dimensional, one antenna here and then one antenna on that other side of the board. Got it? So in total there will be 6 antennas required, although on this two-dimensional board I am showing you 4 antennas only. This is a hypothetical question. On the earth we cannot place antennas of very great height. There are many issues related with that, but for this hypothetical question anything is fine. Okay, now how these antennas will give the coverage of the signals, the coverage of the areas. For this antenna, let's say we draw the diagram like this. For these two antennas, this is the picture for this pair of antennas. Okay, keep in mind there are 6 antennas, but I can draw here only a 2D diagram. What is happening, if you consider the height of this antenna as HT, and this is having the radio horizon as DT, then same thing is with this antenna. Its height is HT and radio horizon is DT. Do you agree? Same happens with all other remaining antennas. And the entire earth is covered. Okay. For calculation purpose, we'll be using the Pythagoras theorem. We know that this distance is RE. This distance is HT. This is RE. This is HT. And this distance is 2dt, where dt is known to us. Dt is almost equal to root 2REHT. Do you remember? Okay, let's apply the Pythagoras theorem in this right triangle. Then what we should write, 2dt whole square should be equal to HT plus RE whole square plus HT plus RE whole square. Fine. 4 dt square is equal to 2 times HT plus RE whole square. Do you agree? Here we are left with 2 only. Dt square can be written very easily. So 2REHT is equal to HT square plus RE square plus 2REHT. Fine. Now we are rearranging the terms. So here we are left with HT square plus RE square. Here we have 2REHT. Here we have 4REHT. This 4REHT I am shifting here. So we will be left finally with minus of 2REHT. Do you agree? And this all equal to 0. It is some familiar expression. Can you think of? It is HT minus RE whole square is equal to 0. This gives you the final answer that HT is equal to RE. Okay. Here we have the height of the transmitting antenna is equal to the radius of earth. Radius of earth is 6,400 kilometer. So actually placing such a great antenna is not at all physically possible. Just for calculation purpose we have done this. Got it? This question gives you the idea that if you want to cover the entire earth using the LOS, line of sight communication, then you need the transmitting antennas of such a great height, which is practically not possible. Then we need another methods, and here comes the role of the repeaters. You note it down, then I'll be explaining repeaters. To extend the range of the communication at the VHF, UHF and the microwave, we use the repeaters. Repeaters accept the incoming signal, amplifies it and then transmit it again. Even in the large buildings, to have the sufficient strength of the Wi-Fi signals, sometimes the repeaters are installed. You might have seen that. On the earth, the TV signals are broadcasted using the towers, and after a certain distance the repeater station is there. It receives the TV signal, amplifies it and again broadcasts it. Got it? Or for greatest communication range, the satellites are used as the repeaters. Since satellites are at a great height above the earth's surface, so they can have the more coverage area. So keep in mind, all the communication satellites are essentially a repeater station in the space. Okay, note it down, then you'll be getting a checkpoint. You may pause there and you may try all those questions for the conceptual understanding. Answer of these questions can be verified at the end of this video. Here is the next question. It's a bit calculative, so you may pause the video here and give it a try yourself. Then I'll be simplifying it. I hope you are done with your calculations. So let's see the solution here. Suppose here is the source of the signal and somewhere here is the receiver. Okay. The satellite is located symmetrically. So the signal will travel from the source to satellite and then satellite will retransmit the signal. This distance I am assuming as x, this is also x, that is symmetry. This distance is given as 600 kilometer above the earth surface. Is it okay? This distance, let's say we are writing as d, this also we are writing as d. Now we can use the Pythagoras theorem. So in this triangle we can do the computation. I'll be writing d square plus 600 square is equal to x square. Do you agree? If anyhow we can obtain the x, we will get the value of d. For obtaining the x, we have another information given in the question. The time taken is known to us, and time taken will be equal to distance traveled divided by the speed. Distance traveled by this signal is 2x and the speed was c, the speed of light. It means x comes out to be ct by 2. c is 3 into 10 to power 8, time is 4.04 into 10 to power minus 3. We are working with the SI system, divided by 2. So doing this computation, x comes out to be 606 kilometer. Is it okay? If x is 606 kilometer, you can feed that value here. It will give us the value of d. Okay, you can do the calculation, you will get some value of d as 85.06 kilometer. Done. Now I am solving the second part of the question here. Pay attention. In the second part, we are using the line of sight communication. So the diagram would be like this. Here is the earth and we have the receiving antenna here. Height of the receiving antenna is HR. We have the transmitting antenna here. Height of the transmitting antenna is HT, and the radio horizon for each antenna is D. The situation was symmetrical. The radius of the earth has been taken as RE. Actually, we know the relation between D and HT. D is almost equal to root 2R HT. We have derived that. So from this computation, HT will be almost equal to D square by 2RE. This is the radius of earth. Is it okay? We know the value of D from this computation. We know the radius of earth as 6400 kilometer. Putting that all data will get it HT as 565 meter. Okay, this is all about this question. You may note it down. Then I'll be taking up the last question of this video. This is a brilliant question. So I again request to pause here and choose the correct options. This question has more than one option correct. Okay, give it a try. I hope you have chosen the correct answers, and the correct answer is option B, option C and option D. Why? Pay attention. If we go for the solution, we remember that dt is almost equal to root 2 reht. Do you agree? We know all the values, so dt will be root 2 into 6400 into 10 to power 3 into 240. Is it okay? We are working with the SI system. This gives you the radio horizon for the transmitting antenna dt. It is around 55.4 kilometer. This is approximated answer. If you remember the actual derivation, then the dt square was ht square plus 2 reht. Check the derivation what we have done, and if you solve exactly for the dt, then it will be ht square plus this parameter. This is the exact value of dt. It means what value we get by this expression, dt will be slightly greater than that. This is approximated value. Actual value of dt will be slightly higher than that. That's why we have chosen the option 55 kilometer also as a correct answer. What do I mean? If this is an antenna and you obtain this dt approximated as 55.4 kilometer, then the antenna can easily cover up to 24 kilometers. This antenna can easily cover the distance of even 55 kilometer, because the actual answer will be slightly greater than this. Got it? So the correct options are B, C and D. It's a nice question. I hope you enjoyed it. Stay awesome. See you again.